These are the 2.1 notes, rectangular coordinate system and graphs, page 3. So we are going to start by using the distance formula. The distance formula comes from the Pythagorean theorem, the sum of the square of the legs of two sides of a right triangle equals the square of the hypotenuse. We've got that diagram up here. Notice that our x sub 2 minus x sub 1, that's the length of one of the legs, or y sub 2 minus y sub 1, that's the length of the other legs. And over here in our equation, we are squaring those and adding them together. And then we take the square root to find the length of that hypotenuse, the third side. Okay. So for example 4, you notice there is a graph there. If you want to graph the points, if it helps to visualize, you don't need to. We're just going to go ahead and use the distance formula up here. So you don't need to, but just a reminder, you guys, those subscripts, the sub 1s and the sub 2s, those do not mean anything more that my x sub 2 goes with my y sub 2 and my x sub 1 goes with my y sub 1. It's not mathematical, it's purely notation. Okay, so I'm going to plug it into the distance formula. Here I've got the distance equals the square root. My x sub 2 is 11 minus my x sub 1 is 1. I'm going to square that quantity. Plus my y sub 2 is negative 1. My y sub 1 is 4. So I've got minus 4. I'm going to square that quantity as well. I get the square root of 10 squared plus, this is a negative, so I'm going to leave it in the parentheses just so I don't mess anything up. 100. Negative 5 plus negative 5 is 25. We get the square root of 125. You always want to reduce these where you can. 125 I can rewrite as 25 times 5. Quick reminder that I can separate that into two separate radicals. Square root of 25 times the square root of 5. Square root of 25, of course, is 5. I get 5 times the square root of 5, or 5 square roots of 5. So in example 5, you will notice that I have fixed my typo. Your notes may have Mannhelm Road and Schiller Avenue typed in. Obviously sent this to my iPad before I fixed that. And so let's figure out what we've got going on here. We are going to set out from Elmhurst, Illinois, located at 00 right here. We make the following stops: intersection of North Avenue and Bertow Road. So these blocks, we're just going to go ahead and count by ones. And to the north, same thing. 2, 3, 4. Okay, so we stop at the intersection of North Avenue and Bertow Road, and then North Avenue and Wolf Road, and then McLean and Manheim, which is right here, and then, Mannhelm, sorry. Oops, I was reading it how I wanted it. And then Mannhelm and Schiller right here. Two different ways that we are asked this question. First, we want the total distance traveled. So straight line linear distance, each of these blocks. Here's 1. Let me go ahead and let's see if we can highlight this if it makes it better. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 blocks traveled along the roads. If we want the distance between that starting point and that ending point, so here's our starting point, that's 0. We have got one side of length 8. see, 6. I stopped counting one too early. And then I've got other side of length 7. If I can count out the lengths of the sides, I don't necessarily need to do the x sub 2 minus x sub 1 and y sub 2 minus y sub 1. So my distance is 8 squared plus 7 squared. We want the square root of that, which gives me the square root of 64 plus 49, which is the square root of 113, which is not anything that's got a perfect square built into it. So we're going to leave it like that. We got the square root of 113, and we need a unit of measurement. We were counting by blocks before, so this stays in terms of blocks. And we've got the square root of 113 blocks. In this situation, we are going to leave this as the radical. That's going to be an exact value. We could convert that to a decimal. We're just going to crank that into the calculator. So I'm not going to do that here.